All right, it's 101, so we can get started.
Sure.
Hi, everybody. I'm Lizzie. I'm one of the Student Learning Hub coordinators at C2 Smarter. Welcome to today's online hub, which is an education and workforce development initiative that offers applied learning and skill building opportunities to help you develop research and job ready knowledge. Today's course is Online Optimization Meets Urban Transportation. Urban transportation networks are complex and dynamic, and as a result, offline planning alone may not ensure effective real-time management. Therefore, this course introduces online optimization methods with a focus on transportation applications. Our instructor today is NYU's Tao Li. Tao is a PhD candidate in electrical engineering at NYU's Center for Cybersecurity. He received his BS in mathematics in 2018, and his research focuses on things such as game theory and multi-agent learning theory, which advance novel frameworks on predictive reinforcement learning for secure and resilient cyber-physical systems. He won the Dante Eula Award for Research Excellence at NYU and has been published at control robotics and security conferences such as ICRA, CBC, and Infocom, as well as journals including TSPN and TRC. And with that, I'll hand it over to Tao to get us started.
Thank you, Lizzie, for the warm introduction. And hello, everyone. So today's tutorial, we're going to talk about the online optimization, a quite important tool in decision-making theory, which we find quite useful and helpful in urban transportation applications. So through this tutorial, we expect ourselves to first understand the difference between conventional offline optimization and online optimization we're going to cover shortly. And second, to know the basic optimality conditions and learning algorithms for online optimization problems. And third, be able to apply the open source Python package SMPyBennets to play around with this online optimization problems. And just let you know, this tutorial is carefully designed at beginner's level. So if you don't understand any part of it, that's not your problem. It's my bad. So just stop me and ask. I'm more than happy to walk you through the details of this math contents. Okay, so before jumping onto the math, let's begin with the motivation. All right. So one important research thrust of mine is to create an urban digital twin with real-time synergy between the physical world and the digital world, powered by this AI and computation modules. So the end product of this digital twin is to facilitate or is to create AI agents to facilitate this information and intervention bidirectional transfer that would bring up this automated data analytics and AI-powered decision-making that help us to manage urban traffics. All right. So in this tutorial, we're going to cover the very first step, the very first task in building such digital twin. That is the information acquisition, how to collect the real-time traffic information and send it to the digital twin. All right. So to collect such real-time traffic information, we definitely rely on some sensing infrastructures, such as loop detectors, surveillance cameras, and we even think about people's cell phones. All right. But among all the sensing infrastructure, the first that came into our mind is actually cameras. Why? Because there are so many of them. NYC has got over 50,000 surveillance cameras across the city. And the map here, the heat map here, shows the distributions of those cameras. And the lighter, the denser the camera deployment is. All right. So as you can see, for some high traffic areas we're interested in, such as Lower Manhattan, downtown Brooklyn, there's almost there are going to be cameras for every intersections. They're almost everywhere. So the task for us is just how to utilize those cameras to collect real-time traffic information. And the bad news is that right now, the current practice underutilize the cameras. So what do I mean by underutilize? So take a look at a real-world example along this Flatbush Avenue, Flatbush corridor, where the Barclays Center is located. All right, so this is quite close to our campus. So what happens is that along this main road, Flatbush Avenue, along the intersections on this main road, there are going to be cameras deployed at those intersections. For example, this red dot denotes the deployment of cameras. And this one, for example, is a camera that is facing south, collecting traffic information south-northern bound. All right. But unfortunately, this camera is fixed to this direction without any tilting or change. So with that being said, the camera can only collect information along one direction and lose information from all others. That's kind of a waste of resources. Why? Because think about this scenario. Suppose there is a traffic accident happening on this adjacent street, a street close to the main road, but not on the main road. All right. Because of this fixed camera, this incident information will not be covered by this camera. All right. So this is the underutilization of the existing cameras, because those cameras can actually be tilted around different directions at different times. So our job is to create a real-time camera tilting strategy so that we can tilt camera at the right time, in the right place. So this is the motivation, the problem we're going to solve. All right. So this decision-making actually corresponds to an optimization problem. So let's say, suppose the action here, A, corresponds to the tilting direction of the cameras. And because, for example, in this example, we have 4 directions in total, so the action set has 4 actions. So our job is to find the best action, A, such that we can maximize our objective function, which corresponds to the number of captured vehicles. All right. So if, suppose the camera, the traffic flow, the traffic condition remain constant across the day, so the number of vehicles doesn't change over time, then this F is static, right? By solving this problem once, we can figure out the best action, best tilting action. However, the real world is not that simple, because this F, this objective function, which corresponds to number of vehicles captured by the camera, this F highly depends on the underlying traffic conditions, which is dynamic and unknown to the camera. So just to give you a sense why this is dynamic, I'm plotting some traffic states, which is simulated using our digital twin. So just to let you know, our digital twin is calibrated using real world data. So in some sense, you can believe this is what's going to happen in reality. So let's first target this upper left figure, where we plot the traffic volume across the whole day on a certain edge. So the link to 1. So this is a certain link in the Flatbush Avenue corridor. So the x-axis is the time axis, and the y-axis is basically the volume. How many vehicles pass through this intersection? As you can see, this red curve shows the dynamic patterns of the traffic volume across the day. And if there is some unexpected traffic incident happens, as denoted by this red plot. So basically, the traffic volume suddenly drops to 0 because the car accident closed the lanes. So the message I want to convey from this plot is that it's really hard for us to foresee what's going to happen in urban traffic conditions. All right. So basically, in this case, we do not know what our objective function looks like. And similarly, we plot another, collect data from another edge and plot the patterns for you. And the message I want to convey is that different streets, different road sections present totally different conditions. And therefore, for different cameras, we need different tilting strategies as well. Those bottom plots are basically plots for traffic speeds, which conveys almost the same message as the volumes. But so I'm not gonna duplicate my argument here. But the key message from this slide is that the objective function, the number of vehicles captured by the cameras, is highly dependent on the underlying traffic state, which is dynamic, unpredictable to some extent. Then when go back to our optimization problems, this becomes a new challenge for us. So right now, we have a static problem where the F is fixed. But in reality, hopefully you are convinced that in reality, this F is actually a dynamically changing objective that is changing with respect to the underlying traffics. So in this case, we have FT. We should append a time index to the F, which means we're dealing with an optimization, totally different optimization problems at each different time step. This is the first, paradigm transition. And the second transition is that in offline optimization, we oftentimes know what the objective function is, and our job is to figure out the minimizer or maximizer. But in the online transportation applications, we do not know what the traffic state is, as I have shown you in the previous plot. What if suddenly a traffic accident happens? And in this case, when we make the decisions, when we pick the tilting directions, we do not know what our objective function FT looks like. So this is unknown. Then what online optimization really does is add the following. So let's say we have the agent, which is the online optimizers, it has to pick an action AT at time t without knowing what the FT looks like. It is only after the action has been implemented, executed, then the unknown environment will return a data point. And in this case, is the number of captured vehicles, FT of AT, to the agent or to the optimizers. Based on this feedback, then the agent would readjust or recalibrate its policy and pick a new action, AT+1, and send it to the environment. And then this process repeats again and again until the end of the horizon. All right. So in summary, in short, online optimization is really about sequential decision-making in an unknown environment, which share the same spirit of reinforcement learning. So if you have you are familiar with reinforcement learning. So in some sense, or actually people agree that online optimization is a special class of reinforcement learning. And when we go to the math, I'm going to explain how online optimization differs a little bit from conventional, traditional reinforcement learning. Okay, so this message one actually summarizes the difference between conventional offline optimization and online optimization we're going to cover in this tutorial. So, and it is because we do not know the objective functions, right? So we're making decisions in an unknown environment. We often also call online optimization as online learning. It's a learning process. You're dynamically adjusting your strategy based on the feedback or data points sent from the environments. So it's also called online learning in the literature. So this is basic, a motivating example, a warm-up. So to summarize, from the first few slides, we have given the motivation why we need online optimization for urban transportation management, and we have highlighted the differences between offline and online optimizations. And now we're going to get into the math. How does online optimization is mathematically formulated, and what are the optimality conditions and the classical learning algorithms for online optimizations? So this second part. And in the third part, we're going to get to some implementation side, and I'm gonna give a very brief, short introduction to a Python package that enables you to play around with those learning algorithms in online optimization. Okay, so first, let me give you a brief overview about the development, the history of online optimization. So because online optimization is a so vast topic, so I'm gonna limit my focus to the convex problems where the objective function is convex. So starting from 80th centuries, before 1949, mathematicians such as Minkowski and Farkas started to look at the properties of convex functions and convex sets. So note that at this point, people are not studying the the optimization problem. They're only studying the convex functions, all right? And then it is until the post-war years did people, mathematicians, and also game theorists start to look at the optimization problems and starting the duality theory of the optimization as to look at the differentiability of those convex optimizations. At the same time, the early day game theorists such as von Neumann and Blackwell start to bring this optimization viewpoint in the context of game theory and try to see how multi-players, multi-agents do optimization at the same time. Moving into the modern era, people start to focus on the algorithms, how to solve those optimization problems, and sort of pioneered by Russian mathematicians Nesterov and Nemirovsky in the 1980s. They have laid the foundations, such as gradient-based algorithms for modern machine learning, right? So for example, the stochastic gradient descent are all based on the mathematical foundations laid down by these two mathematicians. And also, of course, there are some other people contributing as well. And it was not until 2000 did people start to look into the online variant of optimization. So before 2000, most of the works are on addressing the offline optimization where the problem is static. And until 2000, people started to look at the online variant, the online component of convex optimizations. And it is generally believed that Linkovich is the one who first coined the term online convex optimization, despite the fact that many contemporary research efforts are happening as well to address similar problems. Okay, moving ahead, going into 2020s, this is when we get onto the stage. So basically, our research focuses on the multi-agent online learning in the context of game theory. So actually, our research is a confluence of the previous 3 research thrusts. So basically, we're focused on numerical algorithms in the context of online optimizations with a focus on the games, with a focus on the game theory. So we're interested in the collective behavior of rational agents in the learning processes. So in this tutorial, we're going to cover this part, what happens in 2000, and briefly touch upon our latest advancement in multi-agent scenarios at the end of the tutorial. So this is the plan. And the reason why there's a continued uninterrupted research interest in online optimization is because it enjoys so diverse applications across different fields. So to begin with, there are applications on bandit problems we're gonna get to in the next slide, and also applications for recommendation systems, for example, online advertising. So these 2 applications are the motivating applications that facilitate the early days development of online optimizations. And moving on, people start to find that, as a generic decision-making problems, online optimization can also be applied to other engineering fields as well. For example, the intelligent transportation system we're going to talk about in this tutorial, the camera control, and also for robotics and 5G cognitive radio networks, there also have some places for online optimizations. Most recently, people from cybersecurity and also find online optimization very helpful to address spam filtering and intrusion detections. And last but not least, online optimization also found its place in financial engineering, where people apply it for auction design and portfolio selections. I'm just giving you a very a glance or a slim glance on the application of online optimizations, and there are a lot more applications from other fields as well. And one important note I want to make right now is that because bandit problem is really the motivating applications that facilitate the online optimization development at the early days, so many terminologies as coming from the bandit problems. So I'm going to stop for a while, digress a bit, and talk about bandit for a while. All right. So what is bandit? If you go to a casino, probably the most straightforward, simplest item that we can play with is the bandit machines. So this is the photos, illustration for bandit machines. So for each machine, there's an arm attached to it. If you pull the arm, then the machine would return some money to you if you got luck. Otherwise, you receive nothing. So this is the bandit machine, bandit province. Okay. So the question here is that we do not know the inner workings of these machines, and we do not know how much money we receive if we pull each arm, right? So this is basically unknown environment we're facing. So at this place, if we adopt this online optimization viewpoint, if we treat ourselves as the agent, as optimizer, our job is to pick the arm AT, to pick which arm to pull at time T without knowing the money we're going to receive. Because only after the AT is picked, the arm is pulled, then the machine will return some money to us. And based on this money and feedback, we're going to change or stick to the arm for the next runs. So this is essentially an online optimization problems. And right now, just to pave the way for our later implementations, I'm going to introduce a very simple bandit arm problems. It's called Bernoulli arm problem. So in this case, let's suppose we have K machines in total and K arms in total. So then the action set for us is basically ranging from 1 to K, okay, capital K. So each arm K would return monetary rewards using Bernoulli distributions. So what is Bernoulli distribution? So basically, we're going to receive $1 with probability RK and receiving 0 with probability 1 minus RK. So it's a binary selection with probability RK. And however, this RK, this Bernoulli distribution parameter, always a mean, RK is unknown. So basically our job is to, by pulling the arm, receiving the monetary feedback to determine which arm has the highest RK, has the highest mean returns. So this is what Bernoulli arm is about. And we're gonna play with this in our later implementation part. But the message here is basically tell you this bandit problem is exactly online optimization problems. And if you replace this arm with camera tilting directions, then it becomes our problem. If you place this arm with the spam emails, then it becomes the spam filtering problems. So all the decision-making problems share the same similarity, share the same essence. That is, you have to pull the arm, you have to make the decisions without knowing the feedback structure, or without knowing the monetary you're going to receive. So this is the bandit problems. And now we're going to some math formulations. So this Band-Aid optimization problems or this online optimization problems can be viewed as a game between the agent, the online optimizers, and the environment and the unknown environment. So at each time step, so we're considering a discrete time finite horizon. At each time step t, the agent would first pick an action at without knowing, the loss function ft. And then the environment simultaneously pick the loss function ft at the same time. The agent only observes the realized loss or reward ft of at. And then this procedure repeats until the capital T, the end of the horizon. Okay. So the agent aims to find a learning algorithm denoted by ALG algorithm that takes into the past observations. So all the feedback, all the data points in the past, then to figure out the next action, AT+1. So this is the agent job, okay, agent's task. Then the question here we're facing right now is that how do we measure the quality of this learning algorithm, right? Because in static, in offline optimization, it's quite simple. The f function, our objective function is fixed, it's static. Then a very natural way to measure is try to find the minimizer, minimizer of the f, that is a star, and measuring how AT+1 is, how close it is to this a star. However, in this online optimization scenarios, we're facing a changing time varying loss functions. So at each time step, you have ft and you have totally different optimizers, AT star denoted by AT stars. So if we were to visualize this, then basically we have this following plot. So from ft+1 till the f capital T, the end of horizon, for each of them, we have a different, we may have different optimizers, right, across this decision-making domain. Then with this being said, how do we measure the quality of the algorithm in terms of online optimization? So one thing we can do is, because online optimization is a dynamic process, right? So one thing we can do is that we stand at the end of the problems, capital T, and look back. So in retrospect, we can compare what has been done. So the decision we already made, ft of at, versus what could have been done. So if I have picked the optimized solution, at star for each ft. And this comparison actually gives, this measurement to you. So for example, we can measure, oh, by the way, this sort of gap between what has been done and what could have been done is called regret in the literature. So one type of regret is called dynamic regret, which measures the difference between what has been done, cumulative loss, ft of at, versus the cumulative loss under the minimizers, under the optimal solutions at at star. So I'm minimizing what has been done and what could have been done in retrospect. So this is called dynamic regret. It is called dynamic because this at star changes over time. So for different t, this a star is different. Another one, a more commonly used regret notion is called static regret. So basically, it measures the difference between what has been done versus what could have been done in average. So what I'm doing here is that we first take the summation of all loss functions of ft, right? So take the summation of all the past loss functions, and we're going to find one single minimizer that averages, that sort of solve the problems, that finds the minimizer for this summation. So in this case, this a is a static one. It does not change over time or different ft. So we call it static regret. So in the literature, without unless otherwise specified, when we see regret, we oftentimes means static regret. Okay, unless people explicitly tell you we are addressing dynamic. Otherwise, always take it as static regret. So the message here I want to convey is that with this regret notion, we can now define the optimality conditions for online optimizations. So that is no regret. So basically, if the time average regret, time average cumulative regret, so basically, this two difference is going to 0 in the limit, then we can see asymptotically in the limit, my algorithm gives the action that is as good as the optimizers. All right. So I don't regret about my decision makings. I don't have the incentive to make different decisions. So that is called regret. in the limit, no regret, sorry, no regret. In the limit, I'm doing as good as the optimized solutions. So this is the optimality condition for online optimizations. And now with this being said, the next question is how to find algorithms that achieves no regret, right? So let's look at the following setup. So first thing we do is that we try to lift the problem from the discrete action set A to a probability space. So we consider a random policy xt, which is a distribution over the action set. So basically, because for example, in this camera tilting examples, we have 4 directions, right? So in this case, the probability distribution over this discrete set is basically a probability vector. So I guess there is somebody for static regret, what is the difference between minimizing the regret or only minimizing the sum of FT? Okay, that's a good question. So let me go back to the previous slide. So the question was, for the static regret, why we have to minimizing the difference instead of only minimizing the second part, right? The cumulative loss. So here's the thing. So so the short answer is that for a given fixed horizon capital T, they are the same, of course, definitely. But this capital T can be infinity. Let me put it this way. All right. For example, using this camera tilting as example, we're not focusing on 1 day, 1 month, or 1 year. We're focused on a lifelong decision making that the camera can adapt to traffic conditions continuously in a lifelong decision making processes. So in this case, capital T is infinity. So in this case, then minimizing this static regret requires a little bit, because after all, if you let capital T goes to infinity, there is no meaning about summing over infinite function classes, right? Function FT. You really have to look at this difference, how this difference changes over this horizon capital T. How does it change with respect to T? So this is my response. In summary, for a fixed horizon, limit horizon capital T, the same. But if you let capital T goes to infinity, then basically the second part, the summation, does not carry any mathematical meanings. Instead, we look at the growth rate or decreased rate of this difference with respect to the T. So this is my answer. Hopefully, I addressed your question. But of course, if you have any questions, we can discuss after this tutorial. And okay, so again, what time is it? Okay, so let me hurry up a little bit. Yeah, so we lift up from the discrete action set to a probability distribution, probability vector. So sum over xt over each entry equals to 1. So basically the message here is that xt is a probability vector. And then we can talk about the expected loss under this randomized policy xt, which is basically a linear combination of FTA weighted by the corresponding weight of fitting that action A. All right. So the benefit, okay, so by the way, just to make things crystal clear, in this case, the algorithm is not outputting an deterministic action. Instead, it is outputting a probability vector, xt plus 1, using previous observations. So the benefit of lifting the problem up to the probability distribution vector is that in this case, ft becomes continuously differentiable with respect to this probability vector xt. So before this lifting, we're dealing with discrete action set. So for ft, it only takes 4 actions, and there's no point talking about differentiability. After lifting it up, then we can start to compute the gradients of f with respect to xt. And the reason why gradient is important because we can consider gradient descent that is originated in static optimization problems. So going back to a very simple static optimization, offline optimizations, one important or one very basic optimization algorithm is gradient descent. So suppose we have static loss function fx, and at each time point, at each time step, starting from the current iterate xt, we go downhill following the descent direction given by the gradient of f at xt. And if we keep repeating the same procedure, we'll keep going downhills and eventually arrive at the minimizers. So this is what gradient descent does. And mathematically speaking, the gradient descent follows the following simple iterative scheme. You apply minus gradient to the current iterate xt. and you get the next iterate, and you keep this procedure. Then if you just sprightly carry this on to the online optimization province, then we get the following scheme. So the only difference is that instead of applying gradient to the static ones, we're applying a gradient descent with respect to each loss function at each time step, ft here. So at the first glance, you may think this is ridiculous because if ft changes over time, then so are the gradient directions, right? So I'm giving you one example here. So suppose ft looks like this, and this is where the first iterate xt is. And then for the first step, you go to the left following the gradient directions. But when you switch to the next loss function, ft plus 1, then the gradient direction is exactly the opposite. Then you go to the right. So if you're like that, we're chasing after a moving target, we're constantly changing the gradient directions, right? So what are we gonna arrive at in the end? Quite surprisingly, I can assure you that this online gradient descent, following this time-changing gradient directions, actually is gonna give you no regret. So basically, in the limit, the online gradient descent will do a good job, as good as those optimized solutions. I'm not going to the lengthy proofs to prove this to you. Instead, I want to give you an intuitive applications or examples of using online gradient descent. So, first thing we do, to make it easier is that we add a entropy regularizer to the loss function. So if you're familiar with entropy, then basically you can see that entropy encourages exploration or disperse the probability distribution over the decision domain. So visually, figuratively speaking, if this black curve is your original probability distribution, the policy xt that you have, then after applying this entropy regularizer, it helps to flatten this distribution. So more probability weights goes to those the boundary parts. Basically, it encourages the agent to explore those actions that is not oftenly picked using the original distribution. So basically, it encourages exploration. Then after adding this entropy regularizers, if you go through this gradient descent procedure and try to do some math, try to get to the closed form updates scheme, then basically we can have the following equations where explicitly we give the math equation, mathematical expression of this xt plus 1. So basically the message here is that with entropy regularizers, OGD, online gradient descent, adjusts these policies using softmax. Okay, so now let's consider the camera tilting examples. I'm going to expand this in the context of camera tilting. So suppose this minus FTA is the number of vehicles you observed using the tilting action A, right? So what it does is basically, if my current action A is doing a good job capturing a significant number of vehicles, then I'm going to increase the weight on the basis of XTA. So basically, I'm adding probability weights to this XTA and given to the XT plus 1A. So basically, I make this action A more likely to be chosen in the next round. And in contrast, let's suppose if this the number of vehicles is relatively small compared with other reactions, then basically after the softmax, I'm going to decrease the probability weights of choosing such actions in the next round. So basically, you can see this is really a sort of a reinforcement. I'm reinforcing the good actions that gives me more number of vehicles captured. So that's why we call it a reinforcement learning. So in the literature, such OGD scheme is also called exploration and exploitation with exponential weights. So basically, the balance between exploration and exploitation is captured or is controlled by these exponential weights. So in short, it is called XP3, which we're gonna sort of play with in our later implementation. So by doing this reinforcement, we're constantly adjust our policy to the current situation through this OGD. And I guess now at this point, it is no surprise to us in the end, the OGD will do a good job, as good as those offline optimizers. Okay, now, so we're finishing the math part and we're getting into the implementation side. So in this tutorial, we're gonna basically walk through a very, very good and relatively complete Python library for online optimization algorithms. It's called the SMPy Bennett. stands for single player, multiplayer Python package for bindings. So I usually just go by PyBandits. So it is a collection of online learning environments and algorithms. So in some sense, you can take it as the OpenAI gem, but in the context of online optimization. So within this library, within this PyBandits library, there are three important pillars corresponding to the three important components in online optimizations. So I just labeled them in the same color coding. So first is the arms. Think about the bandit machines, which determines the loss function or the reward function ft. So this corresponds to the unknown environment in our online optimization setup. The second one is the policies class, which corresponds to the agent, the optimizers, which determines which algorithm you're going to use to update your action using the data point sent back from the environment. And the third class is the bridge, which connects the arms and policies that facilitate the interactions between these two modules. So this is basically the three important classes in this PyBandits library. And talk is cheap. Let me just show you the code. So let me stop sharing this. And now I'm gonna jump to my collab project demo to show you how you're gonna play with the online optimization using this PyBandits algorithm library. Sorry. So the goal of this demo is to basically walk you through a complete process of constructing this bandit problems or constructing this online optimization problems yourself. We're gonna define, launch, and then evaluate the results of this numerical simulations. So to begin with, we have to import this PyBandits package from Python. And one important note here is that remember to downgrade your NumPy version to this 1.23.1. So I have tried this myself. If you're using the latest version of NumPy, then this is not compatible with some of the algorithms from this library. So be sure to downgrade your NumPy. And these are some preparations for plottings. The important thing here is that remember first to import from the environment class a evaluator object. So here evaluator is like the env class in OpenAI Gem, which helps you to wrap up your environment interactions, which we're gonna get to later. And this is also some preparations for plotting. A second class is the arms. So from this and PyBandits arms, we're gonna import this Bernoulli arms. So basically so remember what we have covered in the tutorial. So the Bernoulli arms basically arm that assigns the reward following a Bernoulli distribution. So with probability 1, with probability RK, you're gonna receive $1. And with probability 1 minus RK, you're gonna receive 0. So this is what the Bernoulli arm is about. And of course, there are many other classes you can choose. And third one is basically the algorithms, the agent, the optimizers. So from this policies class, we import every one of them. Okay, we import all of them. So these are the three sort of warming up stage. We import the environment, we import the arms, and we import the policies. And now we're going to get to the problem forming up stage. So in this case, the capital T, the horizon of decision making is set to be 2000. And it's because we're using a stochastic algorithm. So basically, we're outputting a probability vectors, this xt, right, from the tutorial. So basically, when we evaluate the results, we need to repeat. We need to repeat experiments, repeat experiments, and report the mean results of the experiments to get rid of the stochasticity. So in this case, we set the repetition as 50. And here, the number of jobs basically set the number of cores used to parallels your implementations. And this 5 pieces wide stationary sequence, this is something about the bandit setup. So this is a little bit advanced. So this basically complicates how the Bernoulli arm is generating rewards for the algorithm. So you don't have to worry about this. This is a little bit advanced. And then what it does is because my computer right now has 2 cores, so I only use 2 jobs for parallelization and setting up the parameters. Okay, so right now we have to wrap up the environment configurations. So we're going to create 2 different bandit problems. So one is simpler and then one is more complicated. So the simpler ones, we first have to specify the arm types, which we assign Bernoulli type. So we just tell the package that we want our Bernoulli arms. And the parameters for this Bernoulli arm is basically the mean, the RK, the mean value, the probability of you receiving $1. So this probability is given by sort of this numbers. So here we're considering 3 arms. So basically we have to specify 3 mean rewards. So for each of them, you just give this list. And now here comes the piecewise stationary part. So for from step 0 to step 399, we're going to using one set of means for the 3 arms. And for the other interval, time intervals, we're going to use another mean reward. So as you can see, let me jump to the visualizations for you. So as you can see, so here I'm just plotting the mean rewards of the 3 arms, colored in different colors. All right. So for example, for this red arms, it will change its mean rewards at the step 1200, change from 0.2 to around 0.7, I think. So basically it says at the step of 1200, the probability of you receiving $1 is increasing, which means your algorithm should tell you to pull this arm more frequently. And in contrast, look at this blue arm. So at the beginning, it really gives you high reward because it has a high probability of sending you $1. But after around 800, it suddenly drops to 0.1. So if your algorithm is smart enough, it should reduce through this online gradient descent, it should reduce the probability of choosing such arms. So this is what piecewise stationary is about. That's the first problem. And the second problem, we can even make the problem more difficult by adding more change points or adding more this, fluctuations to those mean rewards. So this is basically another under the same setup, but just adding more breaking points to the mean rewards. Okay, going back to our problem setup. So we set up the first problems, we set up the second problems. The second problem is more difficult. And then we combine them together as the environments we're going to deal with in this implementations. So one important note here is that when you set up the configuration, make sure that your list of number of arms is the same as the list of number of means. All right. So you cannot create 4 arms with only specifying 3 mean rewards. It's not going to happen. So after doing this, then basically you tell the package, tell the library which type of bandit arm you are playing with. And now it's time to pick algorithms. Okay. So even though we only have covered this EXP3 in our tutorial, but there are a lot classical algorithms such as upper confidence bound, UCB, Thompson sampling, Cal divergence, UCB, and so on and so forth. So of course, we're going to cover it one by one, but the one good benefit of having this package is that package will tell you how to play with each of these algorithms. So the thing you do is basically you create, let's say we're playing with KL UCB, then you basically type in KL UCB and have a question mark, and you run it. Then basically it tells you what it does and how to play with it. And of course, for the detailed mathematical expressions, you have to go to the original paper, but at least this help page get you a sense of how to set up the parameters. And now we're gonna list all the algorithms we're gonna play with. So to begin with, let's first look at the first algorithm that we add to the policy classes. So for each algorithms, we have to specify its archetype. For example, we want to play with XP3++. So basically, this is an advanced version of XP3. And the reason why it is advanced, because in this case, you don't have to specify the parameters. It's self-adaptive. And for other algorithms like UCB, KL UCB, Thompson sampling, you do have to specify some parameters. And these parameters, you either go to the paper, read yourself and figure out yourself, or you go to the help page of this library, and it would give you a sense how to select those parameters. So I'm not going to details of each one of them. So just want to say we have picked 27 algorithms from the packages from the library. So that's the reason why I like this library, because it's relatively, I would say, maybe I'm biased, but I would say it's most complete collection of existing online learning algorithms. So after specifying those policies, we're going to complete the configurations. So remember, we have figured out the environment, we have figured out the arms, and now we have figured out the policies, and then it's time to wrap up all the environment configurations. So in this case, we have to specify the horizon, repetitions, a number of jobs, CPUs for parallelization, and your environment setups, your policies, and some breaking points. So when you have specified each of them, then you have this configuration. And then the important thing for you is to pass this configuration to the evaluator class. So I'm going to get into this part in later. So first, we create a hash value for this configuration. And then these are just some preparations for, sort of storing the results. So basically, I mounted my Google Drive to this Colab and specified the directory where we want to save those plots and results. And the most important thing here is pass this configuration file to the evaluator. So use the evaluator class to wrap up this configuration and it becomes an evaluation class. And this evaluation is basically the environment, the complete environment, including the arms, policies, and interactions, as we have seen in the tutorial. So this gives you a complete environment for playing this online optimizations. And once you have this evaluations, now we can start to solve the problems. So first, we're gonna take this evaluation and extract environment ID. For example, we have two environments. One is environment 0 and one is environment 1. So from the environment 0, we pass this ID into this evaluation and give it name it as envy. And then basically we can start to run this name envy. So this envy is obtained from the evaluator class. And then we simply run evaluation.start one envy and then attaching the environment ID and the environment setup, and then the algorithm will kickstart automatically. All right. So because we have 50 repetitions in total, and which takes in total, I think it's 22 minutes. So I'm not gonna run it for you in this tutorial. Instead, I'm gonna just walk you through the results we obtained from this evaluation. So to begin with, let me see, rechecking. Yes. So to begin with, this is the visualization of how your bandit works, how the Bernoulli arm looks like. And then after running environments, the first thing we're looking at is definitely the regret, the cumulative regret for each of the algorithms, right? So let me see, how can I enlarge it a little bit? So basically, this is the EXP3, the algorithm we have introduced. As we can see from this plot, it is not doing a very good job compared with other algorithms in the forefront. And the second thing we care about is basically the running time, how efficient those algorithms are. And in this case, this is where XP3 is. So even though it's not doing a good job in minimizing regret, but at least it does it in an efficient manner compared with some other algorithms. And third thing we care about is memory consumptions. And this is where our XP3 is. So I would say XP3 is quite a seminal SOTA algorithms for bandit problems. So it achieves very efficient computation and use very mild memory consumptions. Okay, finally, I want to visualize the cumulative regret that we have defined in tutorials. So basically, these are the plots for the cumulative regret. So the x-axis is the time step. The y-axis is basically the regret, the gap between what has been done and what is optimal in retrospect. So here, as you can see, using this brown line as the fault line, as the cutting edge, lines above it does not achieve no regret because as time goes by, they are still soaring up. So they're not stabilized. Whereas for lines below it, as you can see, they are almost stabilized as time goes by, which means as t goes to infinity, the increasing of this regret does not catch up with the time increasing. So in the end, the average regret would go to 0. So this is a message I want to convey. Okay, so this is a simple demo of this PyBandit packages. Just to remember, the one message you want to convey with this demo is that you only have to know the 3 important classes from this library. One is the environment, and in particular, this evaluator. And second is the arms, where you pick, set up how the loss function is configured. And third one is the policies, for which you select the algorithm you want to play with. Now, one sort of side remark is that oftentimes in engineering, let me go back to my tutorials. So oftentimes in real world engineering applications, such as our camera tilting, the exact setup is beyond this where's my, the exact setup is beyond this pi-banded package. So for example, we have this multi-camera tilting, right? So this is not just a one agent play with one arms. We have multiple agents play with multiple cameras. And what's worse is that our online learning has to be connected to some AI modules that do data estimation, data imputations, and predictions. So in this sense, I would say, if you really want to play online optimization for your own problems, you probably have to write code yourself. And this pi-banded packages only helps you to be familiar with some SOTA algorithms, and you still have to configure yourself to make it, applicable to your own problem setups. Okay, so I want to use last 5 minutes just to wrap up my tutorial and point out some future directions and challenges that are awaiting us. So first, as we see that at this moment, we are pretty much familiar with how to control one single camera to do real-time tilting, right? But in the real world, we have multiple cameras, right? So the key challenge here is how to coordinate those online learning agents so that they can cooperatively maximize the information collection. So one of our research thrusts is to create this correlated online learning where each agent's learning is coupled with another. So how do they couple? Well, quite simple. So let's say we have K cameras in total, and each camera picks AK from the action set, and then they have this joint loss FT that is influenced by everybody's decision making. So one of the easiest way to achieve this correlation is basically to do a multi-agent gradient descent. So basically, each player is concurrently applying the gradient descent, but only apply this partial derivative to the joint loss. So basically, the correlation is achieved by having this FT, this joint loss. But the key challenge here is how to evaluate this gradient with respect to FT, because FT takes in all cameras' tilting directions. But at the single camera, at a single agent, we can only access to the number of vehicles, to the feedback that is under our control. So how to infer other people's decision-making, other people's loss, other people's actions is the key challenge in this research. And if you're interested, you can go to our paper, which we're going to list at the end of the tutorial. Just want to give you a sense how powerful, this multi-agent online learning is. So here is our problem setup where we care about, the driving risks associated with the number of vehicles in the Flemish corridor. And this is basically the risk prediction in our digital twin using those real-time collected traffic information. So basically, let me tell you how to read this. So basically, the darker, the more riskier the street is. So basically, we use the digital twin to predict the next 5-minute driving risks on each street, on each road sections. And this risk prediction is highly accurate, and the error is below the 10%, which could give the traffic management center a very good sense about what's going to happen in the next 5 minutes, which prepares them for some proactive management. And finally, I want to wrap up using the single table that summarizes all the key points of today's tutorial. So basically, we're jumping from offline optimization to online optimizations where the loss functions are totally unknown and dynamic changing. And second, because the problem setup is changing over time, so we're focusing on sort of a regret notion that measures the difference between what has been done and what could have been done in retrospect. So one interesting finding is that we just blindly apply the classical gradient descent in the context of online optimization. It still does a good job. It still achieves no regret. And finally, we have introduced the SM pi bandits for you to get familiar with some classical SOTA online optimization algorithms. So there are some extended readings for you. So if you want to know more about online learning and optimizations, I would suggest you go through this textbook. And if you're interested in those applications, intelligent transportations, then I would refer you to some papers that are written by us. And I would thank our collaborators for their hard works in these 2 projects. And I will stop here and I will welcome questions from the audience. And actually, I do see one from the chat, I think. Sorry, you are in, oh, I'm sorry. But anyway, I just finished. Yeah, thanks, Tang-Yu, for calling this out. Yeah. Okay, so any questions from the audience?
While you guys are writing your questions, or you can also unmute yourself. I'm also just quickly going to put the broader Student Learning Hub link in the chat for everybody.
Okay, we have question here. Oh, okay. Yeah,
That might
that's
have been me.
easy. Yeah, no worries.
Hi,
Okay, so but if you have questions later, you can just contact me through my email, which is tali@nyu.edu. I'm more than happy to continue our discussions. All right.
I
So
think Kamal has a question.
Hi.
yes,
I had a couple of questions
yes,
actually.
please. Yes, please.
So I'm actually like new to this field, but I have like my research work that I need to like, work in optimization field. So I have some basic questions.
Yes, please.
So first is that, like how do we decide as per our problem statement, like what should be our state, action, and reward?
I see. Mhm.
And when we like is it that we have to go through like some mathematical formulations for that, and when we are trying to bring novelty in our work, so I mean, how do we do that in the optimization field? Is it through the algorithms or through some mathematical formulations? And then, like, as you talked about multi-agent, so why can't we, use single agent reinforcement learning
Uh-huh.
method? And like, how reliable is, I mean, reliable as well as scalable is this online learning
Learning algorithm.
method that you are telling? And
Okay.
because I was also going through like mixed integer linear programming method, so I
Mhm.
was thinking that um, how reinforcement learning will be a better approach, or like from your end, I would like to know, like, is it like a better thing that if we use a hybrid approach of mixed integer linear programming with reinforcement learning?
Mhm.
I mean, so yeah, so
Yeah, thank
sorry,
you.
a lot
Thank you
of
very much
questions.
for the questions. But let me first sort it out because you have asked multiple questions. So first
Yeah.
question is, how do we set up this optimization problems? Do we have to go through some mathematical formulations, right? How do we determine the state, action, and rewards for our
Mhm,
optimization for our learning, right? So this is the first question. And second question is, why do we use this multi-agent learning instead of single agent, and how scalable it is when we consider real-world applications, I think.
mhm,
And third one is gonna be because you worked on integer programming, and I guess you must have come across works that people use learning methods to augment or improve the traditional programming approaches. And the other question is about how do we look at this integration between learning-based methods and the classical optimizations. Okay, I think maybe for me, let me start with the second question because this is most immediate, very easy to answer. So the reason why we don't use single agent reinforcement learning is because the scalability issues. So right now I'm just giving you 4 cameras, right, to control, and it's relatively okay to use a single agent controlling those 4 cameras. And in this case, the action set is gonna be 4 by 4. 4 cameras, and each camera got 4 directions, right? Gonna be 4 by 4, 16 possible actions for the single agent. But now I have told you, right, at the beginning of the tutorial, we have got over 50,000 cameras in OIC. If you're gonna use single agent reinforcement learning, you're gonna 50,000 times 4 this action space. So basically, the curse of dimensionality when you apply single agent reinforcement learning to this, multi agent network control problems. So the reason why we use multi-agent is that we can assign agent or learning agent to each of those cameras. So basically, each agent only controls 1 cameras. All right, and our coordination is achieved through this correlated learning device that we have developed. So basically, in this case, is totally independent learning. So everybody works on their own problems, and the correlation is achieved by this joint gradients. And in this case, it is easily scalable to any size of networks. So basically, once you have a new component joining, you just assign a new learning agent to that component without worrying about the rest. The rest are already set up. So this is the first answer to your second question, right? My answer to your second question. So the reason why we don't use single agent reinforcement learning. And hopefully I have convinced you. Okay, then going back to the very first question, how do we determine the state, action, and reward setup for our learning problems? Okay, so then the short answer is then you have to go through some mathematical, thinking. Let me jump to our at the very beginning of the tutorial where we talk about this camera tiltings. So in this case, the rewards is often dependent on the objective you want to achieve, right? So in our case, what we want to achieve is basically capture as many vehicles as possible, right? To maximize the number of captured vehicles. And in this case, the rewards is directly associated with your objective. Then we just basically set the number of vehicles to be the reward. The actions is basically the sort of the control commands available to you, right? So in this case, the control commands available to us is basically different directions. So this is how I set the actions. Then the question is, how do we set up the state? So this is a very interesting question because there is a complete and independent research on state space design for control theory. So basically, but the short message is here, the state has to be something relevant to your reward functions. So basically, it is the state and your action that jointly determines the reward. So mathematically speaking, when you look at your problems, you just to figure out, except your actions, what else is influencing your reward, is influencing your objective. And this what else is basically your state space. So this is the message I want to convey. So this is the answer to your first question. And now finally going to the third question, which we are not very familiar with because mixed integer programming, we use it, using some Python libraries. We have played with it, but I have no idea, mathematically what is going on. But my take would be, it is very promising to using the learning methods, not necessarily reinforcement learning, any machine learning methods to reduce the dimensionality of your mixed integer programming. And then after this dimension reduction, we can make the resulting programming much more manageable, much more tractable. And then we can apply the traditional mixed integer programming. So the reason why I'm saying this is because there is pros and cons between this traditional approach. So pros is that we have mathematical certified guarantees, the optimality guarantees, sensitivity analysis, and all those mathematical results and bounds, which is nice. But the downside of mathematical programming is that it does not scale very well to real-world large-scale problems. So that is why we have to elaborate, sort of leverage machine learning techniques to first reduce the problem size, to reduce the dimensions, and then apply our traditional, or we say conventional mathematical programming approaches so that we get best of two worlds. So this is my take. Thank you.
Thank you so much. Yeah.
Thank you.
And I would also like to connect with you maybe via email, like for further clarities.
Yeah, sure. I'm more than happy to continue our
Thank you so
conversation.
much.
Yeah.
Thanks.
Okay, we have another question, I think.
Yep.
What is the advantage of MAB compared with reinforcement learning? That's a very good question. Actually, I promised, I'm gonna highlight the difference, but I haven't got a chance to. So if you are, let me first go to this, this plot. So if you are familiar with reinforcement learning and a particular its mathematical background, then you will know that the current reinforcement learning algorithms, such as policy gradient, Q-learning, all rest on a very important statistical assumption. That is, the state space follows a Markovian decision process or Markov decision process, where the previous state, whether the next state depends only on the current state, not on the previous states, right? So this is a Markovian assumptions. And this assumption is a little bit restrictive in a lot of engineering applications because, for example, the traffic states, they oftentimes do not follow this Markovian transitions. For example, this unexpected traffic incidents, right? So you suddenly just drop to zero from a point around 1,000 and suddenly recovers to 2,025. 2,500 after this, the lane reopens. So basically, sometimes we do not have, at least theoretically, we do not have this Markovian assumption. And then in this case, our online optimization comes as a rescue. So the advantage of this MAB problem is that we do not impose any assumptions about how the state is generated. So we just assume that there is a unknown environment. Where is my plot? We just assume that there is unknown environment that generates this FT independently of the actions. So in some cases, so in some cases we have this adversarial bandits where we think the unknown environment is picking the worst case FT, the worst case loss functions based on the previous actions. So basically, essentially, again, played with the two players. And this assumption is much stronger than the reinforcement learning, which assumes a neutral one, which gives you the states following a Markovian processes, right? So in this case, to sum up, online optimization or bottom-up bandit just drops this assumption on this Markovian state transition. Instead, we assume that there is no fixed pattern, no statistical assumptions on how this FT is generated. Our job, or let's say the agent's job, is basically find an algorithm that to achieve no regret in the end. So this is the advantage of this MAB compared with reinforcement learning. So I hopefully have convinced you. Yes, but just one more. Sorry, one more side note.
We're going over, so let's wrap it up soon.
I'm sorry.
We've gone over a little bit, so yeah, if you want to just have some final thoughts, so we can wrap
Final thoughts. Yeah, final thoughts. So yeah, sorry. So final thought is that both online learning and the sort of MDP-based reinforcement learning is considered as a special cases of reinforcement learning, which, broadly speaking, a generic reinforcement learning that make decisions through trial and error. So this is what reinforcement learning defined in broad terms. And what you have talked about based on MDP and what I have talked about online optimization, they are both special cases of this reinforcement learning paradigm, the broad reinforcement learning paradigm. So they're not, against each other. They're just addressing different problems. So I hope this would address your questions. And I will say with that, I thank you very much for all your questions. And just go to my website or contact me through my emails to continue our discussions for all to have your thoughts with me. Yeah.
And to wrap up, thank you, Tao, for your presentation. That was very lovely. You're getting a lot of compliments in the chat, which we love to see. I'm going to put in the chat as well the registration link for our next course, which is Causal Inference, Difference in Differences Regression, and its application in transportation research, which is next week, November 15th at 1 p.m. Hope to see you there too, and have a good weekend, everybody. Thank you.
Thank you. Thank you, Lizzie.
Bye.